This is our second video looking at the tutorial problems from the vectors notes for mechanisms and structures. In the first video we tackled problem 1, and in this video we'll look at problem 2, and we'll be using largely the same approach, and I'll explain everything I'm doing, but maybe not in as such a detailed way as in the first video. So if there's anything that seems I've made an assumption, go back and watch the first video, because that takes a few more steps to explain everything. However, I will do my best to make sure it's absolutely clear. The second diagram we're given, again, has two forces, like all of these problems, and they're pointing, one's pointing up and to the right, one's pointing down and to the left. But the problem remains exactly the same as in problem 1. We have to redraw this diagram with the forces drawn at correctly measured angles and in proportion to their size. We have the matter of picking a scale for this diagram as well. So in question 1, we picked a scale of 1 centimetre to 1 Newton. Now that would not be a sensible scale here, because we'd have to make a 60 centimetre line and an 80 centimetre line. So instead, what we're going to do here is say our scale will be 1 centimetre is equal to 10 newtons, which means our 60 Newton line will be 6 centimetres long, and our 80 Newton line will be 8 centimetres long. Again, manageable sizes, which we can include in our page. So let's draw this in. We'll start off with a starting point of a small cross, and we'll also put in a dashed horizontal line that we can use as a point from which to measure our angles. So we'll put this in across here. So drawing that in, we now want to draw in each of our vectors and draw them to scale as well. So the first vector, we'll take this 60 Newton vector here. We have to measure up from the horizontal line an angle of 60 degrees. And again, this is something you do in paper with the protractor, slightly easier on the whiteboard. With a 60-degree angle, we line up our ruler with a starting point, and I'm going to draw in a 6 centimetre line here, because that is what is required of us. So that is our first vector. This is a 60 Newton vector, and the angle is 60 degrees, as we've accurately measured. Going back to our diagram, we see we've got another vector. This time it's 80 newtons, so it'll be 8 centimeters long, and it's acting down and to the right at 20 degrees. So again, we get angle measured. This is 20 degrees down from the horizontal. We line up with our starting point, and we'll draw in a vector of 8 centimeters length to represent our other vector. So this is 80 newtons, and the angle is 20 degrees. So what we've done so far is exactly what we hoped to achieve, which was to represent a diagram accurately to scale. Now we do the same step of the procedure as last time. We're going to draw in both of our vectors starting from the end point of the other vector. And just before I do this, I'm going to just move our 60 newtons away from there, because it's going to get in the way in a second. Since my rule is already set, this time I will draw in the blue vector first. So I can line up a 20 degree downward line from the end of the red vector and draw in a line parallel and the same length as our blue vector. So 2, 8. Pointing downwards, we include this here. And we want to have a line joining those two that points upwards at 60 degrees, and hopefully is going to be 6 centimeters long as well. Fortunately, as we line this up, you can see it's going to be. We won't always achieve perfection when we do this, but we want to get something that looks pretty good. And where these two lines meet, where I'm drawing this red line to join the end of the blue arrow, where these two arrowheads meet, That is going to be the end of our resultant. That's the overall direction of these two forces combined. So again, we take our ruler and we're going to draw a line from our starting point to our ending point, and that line will be our resultant vector. So we try to be as accurate as possible to the nearest degree. You could say, I think 29 looks about right. It's good to be as precise as possible, but we can only be so accurate when we're doing things, even when we're drawing like this in a computer, and certainly by hand. So we'll draw in our resultant with a green line here. While I've got my ruler down, I'll have a measure of it, and I count 1, 2, 3, 4, 5.25 centimeters, maybe something like that, 5.25 centimeters. So I'll say that's the length of the resultant, 5.25. We've measured the angle as we drew it there. We'll do this separately with a protractor. That's 29 degrees. So arrowhead in here. So the resultant our magnitude is 5.25 centimeters. So we know that every 1 centimeter is 10 newtons. So that is the same as 52.5 newtons. Now, if you're doing this problem, you get a slightly different answer. That's normal because we have got different ways when we're measuring at paper, going to make the thickness of a pencil, the precise holding of a ruler and a protractor, going to give us slight errors. In the direction, I'll write this in the shorthand way. So we could say it's 29 degrees above the negative direction of the horizontal line, so the 29 degrees above the line pointing left. Or I could just write as shorthand. I could say it's going to be 29 degrees from up to that line there. And that immediately tells me what you mean by that as well. So if we want to write it in full, we would say 29 degrees above the negative direction of the horizontal, but that little sketch I've done there also represents it. And of course, we've clearly represented it on our diagram as well. The final part of the question again is to find the equilibriant, and exactly as before, the equilibriant is found by going back to our starting point and drawing a line in the exact opposite direction. So rather than up 29 pointing left, we're going down 29 pointing right, and we draw a line that's the same length, so 5.25 centimeters. 1, 2, 3, 4, 5, 5.25 centimeters there. And this is our equilibriant. So I can say it's also 52.5 newtons. It's also an angle of 29 degrees, but down and to the right this time. And for completeness, I could write this over here. Equilibriant has magnitude 52.9 newtons and direction. I will write it in our shorthand way again. This dashed line represents our horizontal, 29 degrees below that horizontal line. And that completes question 2. Everything we need to do to find the resultant, the green line, and the equilibriant, the orange line.